Hello. In this module, we'll talk about heat and work. We already talked about energy in the last module. So we'll spend some time relating heat and work to energy and benchmarking each of them. So let's begin with heat. Almost all of us understand heat from our daily life experience. Suppose I take a system, let's say a block of copper, and I start lighting a candle underneath it. So if this is my system, and we draw the boundary very carefully all around this block, we know the system's energy is going up, right? Because we know what energy is. E equals Ke plus Pe plus Eu. Ke and Pe are not changing, but we know the molecules will start vibrating faster because we can touch the solid and see it's getting hotter. So obviously, the energy is going up because U is going up. So something must be crossing the boundary. Some energy must be crossing the boundary, and that's called heat. So what is heat? It's represented by the symbol Q, measured in kilojoule, or the heating rate. We'll still call it just heat, Q dot, which will be in kilowatt. Kilojoule per second, which is kilowatt, is what? It's energy in transit. It is energy in transit driven by temperature difference. It always goes from the hot to the cold zone. So what is the bare bone things we got to know about heat? You will have a future class called heat transfer just on this concept. First of all, we understand that the heat, the energy transfer because of the temperature difference will be kind of be higher if temperature difference is higher between the system and surroundings, which is obvious. If the area of contact is higher. Also, another important factor is the time. If you take longer time, the heat transfer will be higher. And finally, insulation, right? It will depend on how insulated the system is. If it's perfectly insulated, if Q equals 0, a system is called adiabatic. You got to memorize this term. So what is an adiabatic system? When heat transfer is 0. It could be because of several reasons, right? One could be that there is no temperature difference, so there cannot be any heat transfer. Maybe the area is very small, or maybe the time is very small. You can run your finger through a flame very quickly because time is so short that not much heat has gone in to do any damage. And finally, if it's very well insulated, heat transfer is 0. So this concept will become useful when we solve any practical problem. Okay. We're just scratching the surface here, so let's take a look at an animation so that we can make some, with the help of the animation, we can build some benchmark. So let's see. We again go back to the same chapter, and where can we find heat? Heat transfer right here. Well, we don't have to really go into the details of different types of heat transfer, but this animation makes it almost obvious. Is conduction. What is conduction? It's a contact sport. When there's physical contact, the higher temperature system, you know that its molecules are vibrating faster, and they will hit the molecules of this low temperature system, and essentially the energy is getting transferred, the molecular kinetic energy is getting transferred through contact, and that's called conduction. We already know that it always goes from high to low temperature. It's almost obvious to us. And we also know at the end, when the temperatures are equal, heat transfer will stop. It's driven by temperature difference. What is convection? Well, whenever it is about the same thing except a fluid motion is involved, then heat transfer happens faster. If you have a convection oven, if there's a flow inside your oven, things will get cooked faster. And what is radiation? So convection is basically a glorified conduction, which is enhanced by fluid flow. You can think like that. And what is radiation? It's a propagation of electromagnetic wave, very complex phenomenon. Just like light, heat can travel. Actually, light is just another part of heat, of the magnetic spectrum. And as you know, radiation means this kind of heat transfer can happen without the help of any medium. It can travel through space. As you know, how energy comes from the sun to the earth, it is through radiation. Again, we don't have to bother about the details right now. All we have to know about heat is that it is transferred whenever there's a temperature difference. But to benchmark, what I like is what is known as the heating value. It's an advanced concept. It's covered in chapter 13 in your textbook. But it's kind of very intuitive concept. All it says is that suppose we burn 1 kg of gasoline inside this chamber. Of course, it'll get very hot. And if you can measure how much heat is coming out, and until the heat transfer stops, in other words, until the temperature cools down to the room temperature, that's called the heating value. For 1 kg of the fuel, how much heat you get. And it has been measured and tabulated for different fuels. For hydrocarbons, it's about this value. For gasoline, it is 44 million joule per kg. For natural gas, it is about 50 million joule per kg, for instance. So this is a good number to memorize, that about 40 to 50 million joule if you burn 1 kg of gasoline. Do you recall how much was the benchmark for our 18-wheeler? A 40-ton wheeler, 18-wheeler, big rig, traveling at 75 miles per hour. It was about 20 million joules, if you recall. So if you remember that benchmark, to get 20 million joules of kinetic energy, to get a truck moving at that kinetic energy, you're burning some gasoline, let's say. Diesel is about the same. You're burning some diesel. So imagine somebody says, how many kg of diesel will you'll need to burn to produce that kind of kinetic energy? Suppose we assume, the engine is about 50% efficient. In other words, in the engine, the diesel is converted to heat, and the heat is then converted to work at a 50% rate, which means right about 1 kg of gasoline will be consumed, don't you think? So it's just ballpark I'm talking about, because half of 44 is about 22. And I think we solved that problem in that animation. We showed that it was about 20 million joules per kg for the truck. How about a cookie? Cookies can be quite calorific. If you do the calculation, I think you may stop eating cookies altogether. So let's go and take a look at the same experiment with a cookie. Well, we don't call it heating value because people call it, calorific value for some reason. But it's the same concept. If you burn the cookie and see how much heat comes out, you'll find that if you go to your favorite coffee place, they write down calories after every item. And these calories are like jumbo calories with a capital C in America. In Europe, it's called a kilocalorie. Anyways, it's about 4.2 kilojoules. So if a cookie has 370 calorie in USA, which means 370 times 4.18, which is about 1.5 or so million joules. A lot of energy here. That's only for one cookie, which is 85 grams. Now, if you convert that to per kg, it turns out to be about 18.2 million joules per kg. So a gasoline will give you about 44, and a cookie will give you 18.2 million joule per kg. Not bad, right? If you run out of gas and you have some cookies in the car, you can figure out how many cookies you need to run your car. Anyway, so our benchmark for heat would be heating value of gasoline, 44 million joule per kg. So whenever you have to discuss energy, heat transfer in any context, think of 1 kg of gasoline. If I burn, how much heat will come out if I burn 1 kg of gasoline? Maximum amount that will come out is called the heating value. Okay, now let's go to the important concept of work. Before that, let me just summarize what we just learned. So for Q is Q dot times T, this is the rate, kilojoule equals kilowatt times second, and the benchmark is 44 million joule per kg of gasoline. Well, now let's think of another situation. Suppose we have a body and we start pushing it with a force F. Let's forget about gravity. Suppose it's in space. We all know we'll pretty soon see that it's going very fast. It will accelerate according to Newton's law of motion. So we immediately know that the energy of the system has gone up. Here it's Ke plus Pe plus Eu, and here now Ke has gone up, and E2 is much higher. Of course, Pe hasn't changed, and U hasn't changed. Suppose the temperature is the same. So just by looking at it thermodynamically, we can say, you know what, the system has gone from energy E1 to energy E2, where energy E2 is much higher. So that means what? We know energy cannot be created or destroyed. So therefore, if we draw a system boundary, there might be some way in which energy is crossing that boundary. And in thermodynamics, that's called work. Well, when you find out exactly the change in kinetic energy using Newton's law of motion, you can show that Ke2 minus Ke1 will be exactly equal force time distance. And that's called work. So in general, we call it mechanical work to distinguish it from other type of work. So this is the formula generally in mechanics we use. We use a dot product, but here let's think one-dimensionally. So the mechanical work, the work we learned in mechanics, is force time distance. So if the force is in kilonewton and distance in meter, then you get kilonewton times meter, which is kilojoule. So the unit-wise, it's consistent. And we get what is mechanical work. So again, what is work in thermodynamics? It is energy crossing the boundary other than heat. Because if heat crosses the boundary, there is a temperature difference responsible. So work crosses the boundary whenever there is a force is successful in making its point of application move, and is given by this formula. Again, you know that from your mechanical background, from your background in mechanics. Now let's expand this concept a little bit deeper. So obviously, if this work is done every second, every second how much work is done is called in mechanics, we call it power. We can say rate of work transfer if we want here. But that's not the main important thing. Important thing is that so that we understand different types of work. So for that, let me just quickly go find an animation. So this is the power I was talking about, the mechanical work. In this case, we can see that it is force time velocity. Why? Because we can say force time distance per unit time and that's equal force time velocity. So that's the rate at which work is being transferred, and that's the mechanical work. Let's go take a look at other types of work. Okay, let me erase the screen. So I'm using this animation, and I hope I can quickly go over each of them without making the video unnecessarily long. The book has all this information. So the power we'll call it work instead of power. In engineering, we can keep on, in thermodynamics, we can say heat and work. It's much simpler instead of all the time reminding. But from the symbol, the dot will remind you that unit will be kilowatt instead of kilojoule. So force time velocity is the mechanical power, mechanical work. We have to divide by 1,000. If the force is in Newton, then you have to divide by 1,000, of course. You get to kilowatt. Now, it's very unlikely that, a whole system is being moved in thermodynamics. Anyway, another kind of boundary movement is more common in thermodynamics. For instance, suppose we have a gas here, and let's say we are heating the gas or something, whatever is happening, and the gas is pushing this piston outwards. You can understand that this piston can do a lot of work. I don't know what is there, but it can push things out of the way. So therefore, work is being done here. In thermodynamics, it's important you understand the direction of the work. In heat transfer, it's very intuitive, right? Heat always goes from hot to cold. In work transfer, you have to look at the system and think, is the energy coming out of the system or going into the system because of this? So imagine you are inside the system. The system is the gas inside, and you are pushing this piston. There will be no doubt in your mind that you are doing the work. Gas is doing the work. So the first thing to understand is that in this case, the work is coming out. That is the first thing to understand, that this work is coming out of my system. And if you understand that intuitively, you're half done in understanding work. Now, how much work is being done? Well, you can simplify that very easily. Think about it. The pressure times the area is the force you're applying. Again, it's the same force times distance. And suppose you go by a distance dx, then in time dt, then that's the rate at which you are doing the work. Well, let's forget the per unit time right now. Just think of over certain time. Suppose you go from state 1 to state 2, then this work, you can write that as equals, so area times dx is basically the volume swept p dv. So if you go from, say, a state 1 to 2, from beginning to end, then the boundary work is given by integral p dv, where 1 is your starting location and 2 is your finishing location, ending location. So this is the formula for boundary work. And again, when you solve a problem, it will become clear that how to calculate. But important thing to understand is that the pressure is the pressure inside the system. It can change, of course. That's why we have the integral sign. But in many cases, it may be a constant. In that case, it's such a simple thing. Pressure goes outside. It's pressure times change of volume. Okay, so that's boundary work. Let's cover different kinds. And mechanical and PDV work together is called boundary work. But generally, mechanical work is almost always absent. So boundary, we routinely call this PDV work as boundary work in thermodynamics. Okay, so now let's take a look at the shaft work. All right, to do so, I have to first get rid of this. Okay, here's the shaft work. Again, this formula should be familiar to you from mechanics, because mechanics cover that formula, 2 pi nt. It is the rotational counterpart of force times distance. If you think about it, the distance, instead of force we have the torque, and instead of distance we have the angle. So if n is the r revolution per second, 2 pi is the angle, right? So in 1 second you're sweeping that amount of angle, because n is the number of revolutions. In one revolution is 2 pi, and this is kind of the counterpart of the distance, and the counterpart of force is the torque, and so that's the shaft work, the rate of shaft work. The torque has to be in kilonewton meter, and n is in our revolution per second, as I have already said, and that produces the shaft work formula. Again, you're seeing the force times distance over and over. So that's why we have so many different kind of work, because what doesn't seem like work, for instance, if there is electricity crossing the boundary, someone came and say, how in the world that is work? But if you think about it for a second, here, of course, suppose this is my system, and inside my system, if I ask you, what do you see crossing the boundary? You may say electron is crossing the boundary, but if you think about it, electrons are being pushed by the electromotive force, and that's why force times distance is exactly how the formula for electrical work is derived. If you find the force, it's at rate, so therefore force times velocity. If you do exactly take the electron's charge and find out exactly what force is pushing it and multiply it by velocity, that's what ends up in the formula, that voltage times current is the power or electrical work, rate of electrical work. Of course, I have to divide by 1000 to get kilowatt. So V is in volt and I is in amp. Then you get the power, electrical work transfer. But it's important to remember, if I have a system, to know if there is electrical work transfer or shaft work transfer or boundary work transfer, you do the following. You clearly draw the boundary of the system and then look for, is there an electrical cable crossing my boundary? And then you know it's electricity going into the boundary. Is it going in or out? It should be obvious. If you are sending electricity, you'll be paying money. If you're producing electricity, you'll be gaining money. So it's kind of obvious. Shaft is also similarly, it's quite easy to figure that out, because in case of shaft work, you'll probably find a shaft is turning a pedal wheel inside the system. You have to supply the power to turn the pedal wheel. So the shaft is carrying energy in or out. You can figure that out. But generally, to recognize shaft work, you will see a shaft crossing the boundary. Nothing can be more obvious. To detect PDV work, you saw that the volume is changing. So therefore, the system's volume will be changing appreciably. So suppose I have a gas moving in a piston cylinder assembly. You can say, aha, that's the case where boundary work is being transferred across the boundary. The sum of all of that is called external work. What do I mean by that? So if I click here, so the external work means, well, let me write down the most common. External work is generally written as shaft work, electrical work, and boundary work. The boundary work is basically the PDV work. Most of the time, mechanical work is not present. So the external work is the sum of the PDV work, shaft work, and electrical work, because this is kind of zero. All right, this is the work that will appear in the energy equation all the time. But if somebody says, what are the all possible work transfer, then that's not everything. There is one more work that I haven't talked about yet, and that's called the flow work. So what is flow work? As you can see here in this little diagram, the flow work is when mass goes inside the system. In this case, mass is being pushed in. Let's say from this pipe, there's some mass going into the system. We'll all agree that mass will carry some energy with it, because if the mass is hot, it will carry more energy than if the mass is cold. But beside that, think of the reason mass is going into the system. So this is a blow up of what's going on at this entrance. So this is the outside and this is the inside. So from the outside, there must be very high pressure pushing the gas in. Suppose inside the cylinder, there is a gas at 1 megapascal pressure. Obviously, gas from outside cannot enter unless the gas is also at 1 megapascal or more. For the gas to enter, the pressure barely has to be equal. It doesn't have to be more than that, as you can understand. Even if there's a force, zero force, this thing can move. So it's not like the pressure outside has to be way more than inside. If you do a free body diagram, you can show you the pressure outside is even 0.0001% higher. There is a net force, therefore things will go in. So for all engineering practical purposes, you can say the pressures are equal at that location where the fluid is entering. So suppose the pressure at this location is 1 MPa. So how much work is being done? Again, just like we did for boundary work, think about it. The force is pressure times area at this location. And if it is going at a certain velocity, that means it goes the distance dx in time dt. So therefore, pressure times area times velocity is the rate at which flow work is being done. Again, the direction is very clear. If the mass is going in, the flow work is entering the system. If the mass comes out, flow work comes out of the system. Well, to summarize, I will introduce what is known as the, let me erase the screen, I forgot to do that. To summarize, I'll just draw a system and introduce what is known as the sign convention. So first let me talk about the sign convention, then I'll give an example. The sign convention mean Q and W are algebraic. What do I mean by that? We'll use Q and W in energy equation. And in equation, you cannot say Q is going in, W is coming out. You have to use sign, plus or minus, so that you know what to add, what to subtract. And by sign convention, which has been well established, we cannot get out of that, to memorize, we use something called Win-Hip. What does it mean? Work in is negative, heat in is positive. So let me quickly give an example and you tell me what should be the sign. Suppose I say here's a pedal wheel and there is some water, and I say, you know, the shaft work we just calculated to be 100, say 1 kilowatt. You use the formula 2 pi nt and you get 1 kilowatt. The question is, should it be plus or minus? Now look at this figure. If of course, the description has to be written, that if somebody says a shaft is churning the water, then it's kind of clear the work is going in. If you understand that, first use the formula, the 2 pi nt. Suppose somebody gave you the torque, somebody gave you RPM, you convert to RPS, and you found it to be 1 kilowatt. First find the magnitude. Then you say, okay, what is the sign? Work in is negative. Therefore, it would be negative 1 kilowatt. Well, suppose there is an electrical heating of the wire. What is W dot electrical? Suppose this is also 2 kilowatt. Somebody says voltage is something, current is something, so you found it to be 2 kilowatts. So what is W dot electrical? W electrical will be negative 2 kilowatt, because again you see that work is going in. What about boundary work? Suppose this is a piston and we find this boundary is moving up, and you calculate the boundary work to be, let's say, 2 kilojoule. I'm not talking about the rate here, I'm talking about, suppose the piston moved from here to there and you calculated the boundary work over a certain time. Should it be plus or minus? Well, as you can see, if the piston is moving out, the system is doing the work. Energy is coming out. So work in is negative, so this will be positive. Of course, plus we don't have to write. So to put it all together, I want you to think about this, and we'll solve a problem of this type, so it will become kind of more clear. Suppose I give you a situation like this, that here's a gas and I have a candle hitting the system, and of course the system here is my gas. So it is clear. Now think in terms of the energy of the gas. Would you agree? As I heat, what is the first thing you will say for sure? If I heat the gas, you will say, okay, it seems like heat is coming into the gas, because this is hot, this is cold. First observable thing will be the temperature there will go up for sure, right? So would you say, if I say in this problem, let's say I say 10 kilojoules of heat has been added. So what is Q? It'll be plus 10 kilojoule, right? Work in negative, heat in positive. So this is positive. My next question could be, what do you think happened to energy? Does it increase, decrease, or remain the same of the gas? Recall, energy is Ke plus Pe plus Eu. Well, you might think that, well, look, the Pe must be going up because the center of gravity of the gas is going up. You may say, kinetic energy, does it change? No, right? It doesn't change, because for the kinetic energy to change, the entire piston cylinder device has to move. So Pe change, as you start solving problem, you'll find gas has such little density that change in Pe is almost negligible. Even if it changes, it increases so slightly. But U, on the other hand, increases like crazy, because think about it. I'm heating the gas, so maybe the temperature is going from 30 to 200 degrees Celsius in a particular problem, because I'm heating the gas. So therefore, U is going up. So therefore, energy is increasing, and it must be coming from the heat transfer, right? Energy cannot be destroyed. In addition to heat transfer, what happens? Would you agree, if this is a gas, it will start pushing the piston up? So my question is that this boundary work, what do you think will be the boundary work? Of course, the boundary work is coming out, right? It's also positive. Should it be greater than 10 kilojoule, equal 10 kilojoule, or less than 10 kilojoule? I want you to think about it. Well, 10 kilojoule of energy has come in by heat, and we know some of it must have gone into raising this temperature because energy has gone up. So what happens to the rest? The rest must be coming out as the boundary work. Does that make sense? Because if I say 10 kilojoules came out as boundary work, 10 kilojoule went as heat, then how in the world the temperature increased? That's a fact. I said the temperature of the gas increased. So does it make sense? This WB can never be more than 10 kilojoule. So this must be the correct answer. WB is less than 10 kilojoule. Now suppose WB is, let's say, 2 kilojoule. Just suppose. That means what? The gas is doing 2 kilojoules of work, right? If you're inside, you're pushing this piston up, and you're doing 2 kilojoules of work. My next question would be, where do you think this 2 kilojoule of work is going? What are you doing? Well, your immediate impulsive answer will be, okay, I'm raising this weight. I'm lifting this mass from this height to that height. In a particular problem, if you calculate that, you will find it will be way less than 2 kilojoules. Yeah, it will be something, but it will be way less than 2 kilojoules. And think about it. So I'm saying, if you do these 2 kilojoules of work, you're lifting not only this mass, but something else. And I leave this topic with this question. What else are you lifting? Replace this gas with yourself. You are the Superman. Oops, I'm so bad in. So you are pushing this up, this piston up. And I'm saying, even though you're doing 2 kilojoules of work, you being the gas, then it is not all going into this mass. It is going somewhere else. Two. Okay, so let me stop here, and I'll solve a problem on this topic in the next module.